Hi there, I'm Mike from Prep 101, and in this primer we'll be going over limiting reagents. Questions about these can be a little bit tricky, so we'll be going over every version that you're likely to see, with some simple examples to train your intuition and then leveraging that into some more formal chemistry knowledge. Without any further ado, let's jump right into it. Let's start with a fairly straightforward example and use this to train our intuition and convert that into something a little bit more formal. The question asks, a warehouse has 80 wheels and 50 bike frames. How many bikes can they make? Now, intuitively, you're probably looking at this and saying, well, with 80 wheels, that's what's going to hold up production. And using this idea for chemistry is going to be very, very useful. Let's take a look at it with this kind of mock chemical equation. If we look at the 80 wheels, and we ask how many bikes could we make if with these 80 wheels? Well, we know there are 2 wheels per bike, which means it's going to be able to make 40 bikes. If we did the same thing with the frames though, we start out with 50 frames and it only takes 1 frame per bike, then that means, based on only the frames, we would be able to make 50 bikes. Obviously, both of these can't be right at the same time. What's going to limit the reaction is the number of wheels. We call the thing that's limiting the reaction the limiting reagent. I'd like to take a step back for a moment and formalize how we did this. To find out what is the limiting reagent, you take the number, or the moles, and you divide that by the stoichiometric coefficient. Remember, the stoichiometric coefficient is the fancy name for the number in front of the species. So for wheels here, that would be 80 divided by 2 equals 40. For the frames, we can do the same thing. That would be 50 divided by 1. Remember, the stoichiometric coefficient is 1. And that gives us 50. To determine which is the limiting reagent, you pick the lower number once you've done that calculation, and we find, therefore, the wheels are the limiting reagent. Let's now see this in a more chemistry situation. A kettle has 0.43 moles of calcium carbonate, oh, that's limestone, in it, and a chemist adds 0.91 moles of hydrochloric acid to it. Then we're given the reaction. The reaction looks unbalanced, so we might have to deal with that. We're asked how much Cl- is produced. And would the kettle be safe to drink out of? Okay. So let's balance this first. That's always going to be the first step. Let's see. We have 1 calcium, so that's looking good. We have 1 carbon, 1 carbon. Oh, the carbonate, the CO3 got broken up, but that's fine probably. We have 3 oxygens on the left. We have 3 total oxygens on the right, so that's looking good. We have 1 hydrogen on the left, 2 hydrogens on the right, so we're going to need to multiply that by 2. And then we have 2 chlorines on the left, so we're going to need to have 2 chlorines on the right. Fantastic. So, okay, now we can look at this and say we start out with 0.43 moles of the carbonate and 0.91 moles of the hydrochloric acid. If you'd like, pause the video and see if you can work out the rest of this question. So the first thing that we're going to do to find out what is the limiting reagent is we take the number of moles at 0.43, divide by the stoichiometric coefficient for both the calcium carbonate and for the hydrochloric acid. When we do this, we find that the calcium carbonate has the lower number there, and therefore it's the limiting reagent. So then we need to find the total moles of, let's see, the question's asking for chloride. So we use that stoichiometric coefficient and the number of moles of calcium carbonate. We start out with 0.43 moles of calcium carbonate. We multiply by 2 moles of chloride, getting that 2 from that stoichiometric coefficient on chloride, and 1 mole of calcium carbonate. And that way, the moles of calcium carbonate are going to cancel, and we come out with 0.86 moles of chloride. Fantastic! We determined our limiting reagent, and then we used the stoichiometric coefficient in order to find the answer. The second part is an interesting conceptual question. Would the kettle be safe to drink out of? The answer here is that it is not safe. The reason it's not safe is because not all of the hydrochloric acid was used. So we still have some hydrochloric acid left. Don't want to be drinking that. Let's look at a second intuitive example here. In this one, we're asked, a warehouse with excess bike frames wants to make 100 bikes. How many wheels must they order? So they tell us that we have excess bike frames, so we don't really need to consider that. We've got as many as we want. We want to make 100 bikes. As a result, we're going to balance this equation and then use the stoichiometric coefficients like we did before. We're looking for the number of wheels, and that's going to be equal to the number of bikes, and then we're going to use that stoichiometric coefficient, those stoichiometric coefficients. So times, always the thing that you care about on the top, so times 2 wheels per 1 bike. We sub in the number of bikes, that was 100. We want 100 bikes. And just like last time, the bikes cancel, and we find that we need 200 wheels. Again, this is an example that you probably could have figured out in your head, but taking your intuition and turning that into math is going to be so useful when you're having trouble figuring out where to go on a chemistry question. Let's go to the next question now. Super fun one. To make fertilizer, atmospheric nitrogen can be reacted with hydrogen according to the following reaction. We have nitrogen, hydrogen, and ammonia, NH3. Given that there is excess nitrogen in the air, how much hydrogen is needed to make 3 moles of ammonia? And they tell us that that's NH3. Like in the last example, our first goal is going to be to balance this thing. You can balance this in a couple ways, and it doesn't really matter which direction you choose. I'm going to do this one, but you could alternatively have said 1 of nitrogen, 3 of hydrogen, and 2 of ammonia. The question doesn't ask for 1 mole in particular, so you can do whichever one you're more comfortable with here. All right, so now we can use those stoichiometric coefficients, those things that we just found, and we're looking to find the number of moles of hydrogen required. We have the number of moles of NH3, that's what we're given in the question, times the stoichiometric coefficients. So let's sub in these numbers. We have 3 moles of ammonia, that's our goal, and the stoichiometric coefficient, well, I have 3 over 2 moles of H2 over 1 mole of ammonia. And again, if you had done it the other way, then you'd still get exactly the same answer here. And when we do that, we come out with 9 over 4. We come out with 2.25 moles of, let's make sure things canceled well. The moles of ammonia canceled out. We're left with the moles of H2. Taking a look at our summary. Remember to divide moles by the stoichiometric coefficients to find the limiting reagents. When you do that, you'll get one number for every single reactant, and you'll want to choose the lowest number. The lowest number is going to correspond to your limiting reagent. And then use molar ratios to convert between species. Remember to put the one that you're solving for on the top. I hope you found this video helpful. If so, check out others like it, outlining the foundations of first-year chemistry in this Primers playlist. Also, be sure to join the Facebook Study Hub group. I'll put a link in the description so you can find it easily. And finally, I hope to see you at our preparation sessions. This is where I'll be outlining how to do so many questions so you can go into your midterm and exam with confidence and earn top marks. Many of the midterm preparation sessions are actually free. That's right, free. Go to prep101.com for more details. Thank you for watching.